So we time shift energy is one question, and there's how do you do that? How can you do that at the scales that make a difference? And what are the practical ways we can actually do that sooner rather than later? So as I intimated earlier, electrons that we get from wind farms, from solar, are nice green ones. We also get less green ones, and we get completely ungreen ones from gas and oil powered power stations. But they're very controllable sources of energy. So our mix of energy comes from all of the above, and we tend to use quite a lot of the non-green stuff because we want to use it all at the same time. So just to kind of sum up pretty much everything we talk about is all in this one graph. So this is data you can get from the internet. There's a site with some links for the data for this if you want to have a look at it yourself. But this is a graph of what's called the carbon intensity of electricity generation. So this is a month in June 2022, so quite recent. So up here is the amount of carbon that was generated in producing a unit of electricity. So that's normally from gas, oil powered fire stations largely. And then we have sunny days or windy days over on the right hand side where we see a factor of maybe 5 less grams of carbon per unit of energy. So just looking at the timescales here, we're about a month. So you can see there's a sort of daily wobble, which is largely down to the daily consumption. So when we need a lot of electricity, there's not enough green electricity, so we use less green electricity. But then you also get these longer scale 2-3 week cycles or periods where you get substantially more green power from windy and sunny days. So you've got a factor of about 2 on a daily basis between, on average, that kind of figure of how much carbon it's cost to make that electricity. So that's why we want to store it. We would like to store it on these short periods, but we'd also quite like to store it on these very large periods, but also in very large quantities. There's not a lot of point saving a little bit of electricity for 30 days or something. So those the carbon intensity and the cost of electricity are actually very well correlated. So many of you may have heard of Octopus Energy. They're a forward-thinking energy company. They have a tariff called the Octopus Agile, which predicts about 24 hours ahead, depending on what time of day it is, what the cost of electricity is going to be for the next 24 hours. And they get that data from the wholesale markets that everybody has access to. So this cost is almost related to the amount of money they have to pay to somebody else for the electricity. So you can see there's obviously a very strong daily cycle. These peaks here where it goes up to, this is quite old, this is from 2020, because the graphs at the moment don't look very nice. So 2020, we can see there's a factor of 5 in the cost of a average low amount of low cost, rather than these sporadic ones. And then every day it goes up to 5 times, fairly predictable. You know when it's going to happen from day to day. And even though you can't quite see this graph here of the carbon intensity, those peaks tends to be at the highest points of these this carbon intensity here as well. And these lower bits tend to follow the general trends. So if you have a very low carbon intensity day like here or here, you tend to get almost free electricity. And sometimes they even pay you to use that electricity because if you make a wind farm and you can't be paid for your energy, the energy companies have to pay you instead. So that costs quite a lot of money, and increasingly will the more the mix of renewable energy that goes onto the grid. So that's quite an interesting thing, but it's actually not that useful because it doesn't happen that often. So in 2021, It happened for 80 hours for the whole of 2021. Perhaps if there was more green energy, it would happen more frequently, but if there's going to be more energy, there also needs to be more storage, and so it's a story that probably won't pan out as many people might think it would. So just looking at some general trends, which is the graph, the more honest graph at the moment. So here's some of the problems, and here's some of the reasons why selling time of use energy and shifting energy around is not particularly popular at the moment. So the agile tariff from 2018 to 2022. So you can only change the cost of electricity twice a year if it's a fixed rate, but if it's a variable rate, you can change it whenever you like within the bounds. And that's exactly what we see here, is that upper limit of 35p a unit is being hit most of the time. And in fact, sometimes and quite often, it's 35p all the time for a variable rate tariff. So this is quite an unappealing tariff for somebody who wants to be greener. However, on a good day, and maybe one day again in the future, we might see it back to this more normal case where we do see this kind of factor of 5 or 4 or 5 between peak use energy and off-peak energy. So it's like economy 7, but it's more agile. So we're working on the assumption that one day somebody will fix this problem, and there is some regulatory stuff from the government that comes in that will probably help the companies avoid these price issues, but also give better incentives to end users, so people with buildings, to invest in something in their building to use greener energy. So we're talking about buildings, so I'm going to skip past the obvious ones, which at the moment, which are kind of, how does the grid solve this? Or how do large organizations building big infrastructure projects solve this? So pumped hydroelectric is the classic. Very large scale, but takes a lot of land, and once you've kind of got a certain amount, you would like to be able to scale that up much more. Compressed air energy storage, which is more scalable. It's arguable how efficient it is. It's quite efficient sometimes, but in basic form, it's quite low efficiency, but it is very scalable. Green hydrogen, again, like a battery, you can generate hydrogen from green electricity. Again, not particularly efficient, but in theory, you can use that and store it, and you can do things like fly planes with it, which are quite difficult to do with electricity. And then, of course, batteries. So there are various kinds of batteries for higher volume, but these are quite expensive things to develop at any scale. There's quite a lot of investment in them, but many of them don't produce anything particularly huge. So just a bit of context for some of these technologies. So this is, I think, from a US site that kind of gives the kind of scalability of some of these technologies for, and as you can see, we've got pumped hydroelectric and compressed air at the right-hand side of that graph, which are probably good technologies, but they're also quite expensive technologies. And they don't solve all the problems of distributing power over the grid. So a bit more context. So in the UK, I think we can get about 2.5% of our daily power requirement into hydroelectric at the moment, which is significant, but it's not that scalable. So we're looking at other ways in buildings, more distributed approaches. So there's house batteries are the obvious one. There's electric vehicles that have batteries in them, which is another one. And there's also domestic hot water, which is our baby at the moment, because water needs quite a lot of energy to heat it up, and we need quite a lot of heat, and we normally heat water up as well. So given that we do that anyway, some of its deficiencies are quite forgivable compared to the others, given that it's a very scalable technology. And of course, domestic heat pumps. So heat pumps, obviously great, but because they don't heat to very high temperatures, you can't really store their energy very effectively. So heat pumps are great, but they will tend to use more peak electricity than other methods. So they're not using the greener electricity as much as even a direct heated system could, that's less efficient. So just a bit more scale. If in the UK, if we heated all our water at the off-peak time and stored it, that would use 12% of the requirement for domestic consumption. If we did the same with heating, which is more difficult, you need quite a lot of storage for heating. This is quite modest and not particularly realistic values. You can get another 24% of the national grid's output into hot water tanks and heat your home from those. The scalability of that is quite difficult, but it's certainly doable. There are other methods of heating, of storing heat. So there are other methods of thermal batteries, phase change ones, but actually they're often compared with water favorably only because water is often not heated up to a very high temperature. Because there's actually a second problem, is that the nuts and bolts of heating up water and storing it at, say, 90 degrees is perfectly safe in theory, but if you want to go and buy a thermal cutout to make a safe system that works at 90 or 95 degrees, you won't get one at your local plumbers, and you probably won't even get one until you go to an industrial supplier. So there's quite a lot of stupid stuff as well to deal with to make this stuff work, which we've been kind of going through, but there's very, very little investment in this area. So something as trivial and prosaic as a thermal cutout that can be electronically set, for example, and meet safety standards, not a massively expensive thing to do, but it's more money than we have at the moment to do it. So we tend to have to revert to industrial solutions for those sorts of things. How long have I got? No more. There was my pun. Didn't really work. So yeah, water is quite an overlooked thermal storage technology. It's a little bit boring. It does involve plumbers. We're not always the most interested in these things in our experience. Well, that is a really bad thing to say. I shouldn't have said that. I was going to tell myself not to say that. But however, we haven't met many plumbers who have been very helpful so far with this. So we are looking really for people like Arup and other buildings engineers people to help us promote hot water as an energy storage technology. And I think that's it. Yeah, no, I've nothing I've left there. Yeah, I should. Thank you. Cheers.